Good afternoon, everyone, and welcome to today's installment of the Safer Sim webinar series. Today, we are going to have a presentation from the University of Iowa. Dr. Joe Carney and Dr. Jody Plummer from the Hank Lab are going to discuss their project that uses a pedestrian simulator. So, Joe, I'll let you take over. I should say, for anyone that does have questions or comments during the presentation, feel free to use the chat box and we will address those um, at a good point in the presentation, or else we will address them at the end of the presentation during the question and answer session. So feel free to use the chat box if anything pops in your head. Other than that, Joe, feel free to start whenever you're ready.
Thanks, Jacob. Thanks for the introduction. And yes, please ask questions along the way. If you have questions, I'm happy to be interrupted along the way and address any questions you have. I'm speaking to you from an unusual circumstance. I had some unexpected family travel, and so I'm out of town. I'm in an Airbnb in Philadelphia at the moment, sitting at the dining room table. So this will be the most unusual presentation I've ever given. But this is work that I'm very excited about that Jody and I have done was led by Pooya Rahimi in our lab and was a Safer Sim project, looking at prohibitive warnings and how we can alert texting pedestrians about dangers when they start to cross roads. This work was conducted, as Jacob said, in the Hank Virtual Environments Lab. Our job is to create realistic, immersive virtual environments that allow for full body movement. Jody and I co-direct the lab. We have both pedestrian and bicycling simulators in both big screens and in head-mounted displays more recently. This work was conducted in one of our big screen environments, and so it's what's sometimes called a cave virtual environment. It has screens that are 8 foot tall. The front screen is 10 foot wide. The side screens are over 14 feet long, and then the floor itself is over 14 feet long by 10 foot wide. So we have 3 screens, a front and 2 sides, and a floor. The side screens are rear projected, and the floor is front projected to give a really an immersive environment. So we study problems using these virtual environments, such as how do child cyclists cross roads in traffic, how do texting pedestrians cross traffic-filled roads, and how do parents teach children about road crossing. It's best to give you a sense of what this environment is by showing you a video. So this is a video that was taken from one of the experiments looking at adults and children and their children crossing roads together. So here we go.
I'm just going to be counting in my head.
Last time after the purple car, there was plenty of space. Let's see. Not yet. 2 cars.
I'm looking forward.
Watch the car. Ready? Let's go now. Our car pass. Okay, back up. That was easy.
So there's a few things I wanted to point out here. So the screen, you may have seen the double image there. That's because we're projecting images for the 2 viewers. So each viewer, we can do this in 2 ways. And so we can either project stereo images with prospectively correct images for 1 viewer, or we can take the 2 streams of images and give one to one person and one to the other person. We track their head with an optical motion tracking system using the helmets that they have on with the markers that are on the top. And then we can give each viewer their own independent prospectively correct image. So what you're seeing there are 2 image streams for the 2 participants. The other thing you'll notice is that the image warps, it distorts as they go forward. To them, it looks correct because the view frustum is correct for their viewpoint. Oh, and one more thing, you'll notice that they're tethered. Part of the problem we have is particularly with stereo, that the front screen dissolves, and so it's very hard to see when you reach the front screen, and we just don't want them walking through the front screen. So what this is about is some research we've done looking at texting pedestrians. There's been a lot of attention brought to texting pedestrians and the dangers that texting while you're crossing roads creates. There were several campaigns to promote awareness about being aware when you cross roads. New Haven, Connecticut, and New York put stencils on the street so that if you look down, it will give you guidance to look up and look at the surrounding traffic. The National Geographic in Washington, D.C., at the lower left there, created cell phone lanes as a campaign to bring attention to the problems of walking unawares. So there's a no cell phone lane and a cell phone lane for those who are distracted. And at the upper right, Improv Everywhere, which is a group in New York, did a prank where they had seeing eye people who would guide pedestrians down the road. You just put on a little leash and they would guide you as you texted to make sure you were safe. As cars are being developed, there's lots of new technologies that are going in. And one of the new technologies is dedicated short-range communication chips that allow cars to talk to other cars on the road. This allows a car to be aware of other traffic that's near and help the driver by bringing attention to dangers that are around them and maybe even stopping the vehicle when the driver isn't responding correctly. One of the, this is so-called V2V or vehicle-to-vehicle communication. And these chips are possible to put in cell phones so that pedestrians could have the same information and know where all of the cars are and where the infrastructure is and what the state of the infrastructure around them is. This is called vehicle-to-pedestrian or V2P technology. And our research looks at how can we leverage this technology to help promote safe road crossing. So what can we do to put into phones to tell them either when it's safe to cross or to alert them when they're making unsafe decisions in crossing roads? So we call these two different strategies permissive alerts, which tell a pedestrian when it is safe to cross a road, and prohibitive warnings, which tell them when it's unsafe to cross. It's like a collision warning or whenever there's an imminent collision or a don't walk signal that tells them don't cross the road. So what I'm going to do is tell you first about a preliminary experiment that we did that was an earlier Safer Sim project, and we gave a webinar about this some time ago. It was published in IEEE VR in 2016 that looked at permissive alerts. So permissive alerts tell a pedestrian when it's safe to cross. We gave this to texting pedestrians and provided them with information in a couple of different ways. So one was to give a shot clock that was on the cell phone that moved along with the text they were typing. And what the shot clock did is as the acceptable gap was arriving, it gave them a shot clock that counted down to the opening of a crossable gap. So this 19 here, this shows that in 19 seconds there'll be a crossable gap. And then it turns green to tell them that now it's safe to cross. When it turns green and it's safe to cross, this is 1 second before the gap opens, it also gives them a visual and an auditory alert. So it gives them a beep as well. So this is an experiment that was a between subject designs. There was a control group that didn't text, a texting group that did pretty rapid fire texting, and then an alerts group that did rapid fire texting and received alerts when it was safe to cross. There was a steady stream of traffic coming from the left side at 25 miles an hour and 35 miles an hour. This meant because cars were coming at different speeds, the gaps were actually changing size as the cars approached the intersection, making it a pretty challenging task. Small gaps occurred more frequently than large gaps, and the gap sizes ranged from 2.5 seconds up to 4.5 seconds. And by that, that's the size of the gap when it's open in front of them. So the gap itself changes as it approaches the intersection, but that's the gap that they actually, the opportunity they have for crossing. The road crossing task involved 3 practice trials and then instructions to cross safely and 20 test trials. We didn't tell them whether or not they should pay attention to the signal. They made the choice about how they were going to respond to the alert. So this is a video from that experiment. So this is the control condition. And again, you'll see the image distorts as they walk across. This is the texting condition. The computer sends them rapid fire texts and they respond. And this is the permissive alerting condition. So you'll see that countdown clock will appear here when the safe gap is about to arrive. And here's a safe gap, and they've gotten a beep on the phone at the same time. In this, you'll see a visualization, so we can replay the simulation after the fact. So this is a recreation in graphic rendering of a simulation. And what we record is both the position of all the dynamic objects, orientation, and then also where the head is looking and where the cell phone is oriented. This allows us to determine when the participant is looking at the cell phone or at traffic or somewhere else. At the bottom, what you'll see is essentially a snapshot of a trial that I'll show you again in a second here. So this is what a snapshot of a trial looks like. This was that graph that appeared there. This graph shows sort of everything that happens in one trial. Here are the cars. This is time down here. These are the time periods that each vehicle is in front of the participant and prevents them from crossing. So in between are the gaps that they can cross the road. This is the trajectory of the participant in blue. And so it shows that they're standing on the side of the road and then cross through a gap and reach the other side. At the top up here, we can see their gaze when they're looking at the phone, when they're looking at traffic, and when texts come in and go out. The key measures for this and for the next experiment that I'll talk about are gap selection, that's the average gap size, the likelihood of accepting a gap, their movement timing, so when they chose to cross through a gap, the time of entry relative to the opening of the gap or to the rear of the lead car in the gap when the pedestrian enters, the time that it takes them to cross the intersection, and the time to spare is sort of the bottom line measure when they get across the road, how much time was there between them and the tail car in the gap. Here is the logistic regression graph that shows the likelihood that they'll take a gap for the different gap sizes. So this is sort of typical form for these graphs. When gaps are small, they're rarely taken. When gaps are large, they're frequently taken. And then the different conditions will show two different properties. One of the things we look at is where the graph is oriented from left to right, that is to look at the threshold for gap acceptance. Oftentimes we look at the 50% mark here. And then also the slope of the curves tells us about how well they are at discriminating large gaps from small gaps. So what we found with permissive alerts was that they were highly likely to cross the alerted gap, and 97% of the time they crossed the alerted gap. This led them to cross larger gaps than they did in the texting condition. And you can see here are the alerted gaps, and you can see the very high frequency here in the texting condition for which they took those gaps. So it improves gap selection. The alert group had fewer close calls and fewer hits compared to the texting group. The time left to spare was similar to the non-texting control group, and the texting group had less time to spare, so they had closer calls. So that's the good news. The other somewhat surprising part of this was what happened to their gaze. What we found was that people in the alert condition looked at the traffic only 24% of the time. In the control condition, they looked at traffic in the 2 seconds before the gap opened and the 2 seconds after. They looked at traffic 97% of the time. In the texting condition, they only looked at traffic 46% of the time. And in the alert condition, they only looked at traffic 24% of the time. So you can see these charted for different time periods here as a histogram. The little blue measure here shows when the alert went off. Primarily what happened with the alerts was they gave a brief glance at traffic just before they crossed. This is the crossing time right here. This is when the gap opened. And so they give a quick look and then they're back to looking at the phone again. So they predominantly look at the phone. So armed with that information, we conducted the current study that I'm going to talk about, which is about prohibitive warnings as an alternative to the permissive alerts that we did in the first study. The goal here was to see, well, can we find another way to maybe gain the same benefit that we got from the permissive alerts, that is safer crossings, better decisions, but maybe not have the as much or much less of the loss of attention and potentially loss of situational awareness because they're looking so much at the phone. So the key question is here, how do texting pedestrians respond to warnings that tell them when it's unsafe to cross? So this was based on an auditory notification that was triggered by the head movement. So when the head moves forward, we detect that and give them a warning if the time to collision or the time to arrival of the next vehicle is less than 2.75 seconds. This experiment was done as a between subjects experiment as the last one. There was a control group, a texting group, and a warning group. The scenario was much the same as the scenario from the permissive alerts. You can see here the cars are coming from around a corner, they appear and they approach the intersection and then they pass the participant at the edge of the road. So there were a total of 164 warnings on 151 gaps in 318 total trials. They crossed the road on 28 trials when they received a warning. On 107 of these gaps when they received a warning, there was just incidental movement. So the head tracker detected a movement forward, but there was no overt motion to cross the road. And on 29 of these, they started to cross before the lead car reached them. And so the alert was, the warning was triggered on the lead vehicle in the gap. And then on 10 of those, they actually crossed the subsequent gap that was behind it. This is a graph actually from an earlier version of this experiment that I put up here just to show you. Here are the trajectories for a whole bunch of trials that were alerted. And you can see here the timing of the alerts. So basically this shows you the triggering that happens to tell us when they're crossing the road. And this is, so they've just barely entered the road here most of the time when they get this alert. So a couple of striking things stood out here. One was that the alerts condition had very much longer waiting time. They had almost twice as long waiting time as did the texting and the control conditions. The texting condition, the texting only, took smaller gaps than the alerted condition, and they were also less discriminating than the alerting condition, so that lower slope on the texting condition. The warning group timed entry less tightly than the control or the texting group. The warning and testing groups were more variable in timing, should say texting, sorry, than the control group. And there were no differences in time left to spare across the three groups. Gaze, it was not quite as dramatic as it was in the first experiment. There, the alert only looked at the traffic 24% of the time. Here, they only look at it 36% of the time. So they're looking more. It's somewhat surprising that they didn't look even more yet. I think part of that is because during this period here, once they've made a decision, they sort of give up looking at the road. And so this is part of where this comes from. But during this period here, the warning itself doesn't tell them what gap to take. It only tells them when they're making a bad decision and starting to cross. So it doesn't provide them any guidance in picking a gap. And so that this isn't even a bit higher is a little bit surprising. But it's the weight of this is what is the biggest difference between warnings and the permissive alerts. On the warning trials, one of the most surprising thing is that once they were warned, the 28 where they made an overt motion to cross, on none of those did they abort their crossing and return to the curb. They always continued to cross. So even though the warnings were highly predictive of risk, no one aborted their crossing and returned to the side of the road when they received a warning. So this is really, I think, the surprising part of this paper. On warning trials, their average time to spare when they crossed the road was 0.11 seconds, which is very, very tight. And then 10 times of those 28 crossings, they got hit. That's 36% of the time. So it's pretty alarming that they didn't observe the warnings. And I think that's one of the key outcomes from this research. So why were the warnings not heeded? We have several possible explanations that we're investigating. One is that maybe because they're in simulation, there just wasn't a sufficient impression of risk. They just didn't feel the risk was severe enough. Another maybe because once they got started and got the warning, even though they had just entered the road, it may be quicker to cross the road than it is to back out of the road at that time. It takes time to stop a motion. It takes time to reprogram a motion. It takes time to get back out of the road. It takes a total of about 2 seconds to cross this one-lane road in our simulator. And so it may actually strategically be better if you get a warning once you've entered the road to just keep going, at least in a one-lane road in our simulator. Another possible explanation is based on literature in the psychological literature about action selection. There's neurophysiological evidence that once an action is selected, alternative actions are suppressed. And so it's less likely you'll take another action once you initiate one. It's a form of commitment that prevents dithering from going back and forth from doing one thing to the next. There's a whole series of experiments, a rich literature on the stop action task, which is a task that usually involves button pressing with a hand when a signal comes up. And then there's a second message that tells them to interrupt that action, that provides information about the challenges in changing actions once you've started an action. Supporting this result, there was a research experiment conducted in 2017 that at IFSTAR, the French research lab, that was also a simulation study that looked at a vibrotactile alert to elderly pedestrians that were non-texting when a small gap approached. And what they found is that, as in our research, that when you received warnings, you made safer crossings, but they still continued to cross in about 50% of the alerted gaps. So the scenario was different. Ours were texting, theirs were not. It's a different population, and their presentation of gaps, they provide one gap at a time, and we provide a stream of gaps. But nevertheless, there is a sort of a consistency in that participants were not responding to warnings on many trials. So the bottom line is it better to use alerts to tell people when it's safe to cross, or to send an alarm when danger is sensed. Part of the difficulty is it's hard to tell when people are making an intention to cross. It's hard to anticipate what they're going to do. Pedestrians stand at the side of the road, and they are a second away from being hit just about all the time. And so judging when they're going to enter, they can move so quickly to get into the road, is a difficult task. Setting a threshold that's going to capture when they are actually crossing, and minimize the number of false alarms. So making sure you don't have many misses and don't have an excessive number of false alarms. These are tricky technical problems in trying to estimate what our pedestrians are doing when they're going to cross a road. I wanted to finish up with another study that we just completed recently, working with Toyota Motor Company, looking at pedestrian road crossing at night. So pedestrians are, road crossing at night is dangerous. Most pedestrian fatalities happen at night. There are a variety of factors that contribute to nighttime crashes. So one is drivers have difficulty seeing pedestrians in low light. Their headlights are primarily casting light on the road, and it's hard to see pedestrians on the side of the road. Pedestrians tend to overestimate drivers' ability to see them. This is what I like to think of as the I can see you, so you can see me phenomena, that pedestrians assume that because they can clearly see the car can see them, the driver can see them. There are a couple of ways to try to improve driver detection of pedestrians. Street lighting and reflective clothing are both important to improve conspicuity of pedestrians for drivers. So what we wanted to look at are the designs for new adaptive headlights. These are independent spotlights that are on the front of cars that can detect pedestrians near the road or as they enter the road. The spotlight directs illumination on them and highlights them to make them more visible for the driver, but it also provides an alert for the pedestrian by giving them a signal that there's a car approaching, and bringing their attention to this car by putting a light on them. So this experiment, this larger study, is looking at how pedestrians and bicyclists respond to adaptive headlights. You see two pictures for two different designs that we're testing. On the left is our pedestrian simulator at night that has a spotlight that's casting light around their feet and then putting an icon in the road to bring their attention that it's dangerous to cross. So as the car nears the intersection, the spotlight illuminates around them, and as it gets close and it becomes dangerous to cross, it provides that icon in the road. On the right, you'll see our pedestrian simulator, and this one we were looked at an overtaking scenario, and so the car came from behind the rider, and as it approached, it shined light around the bicyclist, the base of the bicyclist, and then also later would put the icon in the road when it got close to passing the bicyclists. So the overtaking scenario, we compared responses to cars that have traditional headlamps with ALS headlamps. And we looked both at having just the box that illuminates light around them and the box plus the icon that puts the red icon in the road. And the questions we asked were, well, how does the bicyclist respond, both to cars that have ALS and when they have cars with ALS, do they respond differently to cars that are non-ALS that come after them? And so does the bicyclist move to the right to give more room for the car car to pass? And does the bicyclist slow down when cars with ALS overtake them? So the scenario was a mixed design. And so there was within subjects factor looking at traditional headlamps versus ALS. And so there were approximately 10 of each that overtook them. And a between subjects factor with different ALS. There was ALS with just the box and ALS with box plus icon. The scenario was on a straight rural road with cars coming in both directions, traveling at 35, 45, or 55 miles per hour. Cars came in opposing directions, had traditional headlamps. Cars that were overtaking had either traditional or ALS. The task was to ride along the side of the road without getting hit by a car. This shows the results from our experiment in a graphic form. We're still doing some data analysis on this experiment, but what you'll see here is these are all of the trajectories for all of the different trials. And so you'll see clusters of trajectories. The colors indicate if it's pinkish, it's ALS with box plus icon. If it's kind of greenish, it's ALS box only. And if it's kind of bluish, it's non-ALS. And so you'll see what we found is those with the box plus icon tended to cluster more towards the side of the road. So there was a beneficial effect of the icon in particular in moving riders more towards the edge of the road, far away from the traffic. We've broken this down into several different phases here. So this is in a pre-phase as they're beginning to approach. This is in a phase just before as they get there and the light comes on. This is when the icon comes on here. This is the passing phase, and this is after they've passed. We're currently following up that experiment looking at a pedestrian scenario where we have a mix of ALS and non-ALS cars to look at how pedestrians make judgments about crossing gaps, much like our other warning systems. So in summary, what we found is that warnings can improve safe road crossing. In all three of our experiments, the permissive alerts, the warnings, and the lighting system, the ALS lighting system, improved the safety of either the bicyclist or the pedestrian. They took bigger gaps as a pedestrian. They were more to the side of the road as a bicyclist. We found some potentially undesirable outcomes as well. So in both the warnings and the permissive alerts, we found there was a reduction in attention to traffic. We also found that there was a lack of responsiveness to the warnings. We're still trying to understand what the underlying causes of these are so that we can find better ways to use the information that we have in order to help pedestrians make safer road crossings. We're interested in investigating the effects of traffic information that's possible given the new technologies that can be embedded in phones, but it's important to understand how pedestrians will respond to these and how we can most effectively present information to them to make them safer on roadways. So I want to thank a whole cluster of people who are members of the lab and former members of the lab who contributed to this work. I want to particularly highlight Puya Rahimian and Elizabeth O'Neill, who were involved in this experiment and did much of the work here. And also Xiaowen Zhao, who helped a lot with the running of the experiment in the study that I presented today. And last, I'm going to give a thanks to all of our sponsors. Our work is sponsored by National Science Foundation, Toyota, the Department of Transportation. We've had past support from the National Institutes of Health, and we're particularly grateful to Safer-Sim for all the support we've gotten for them to do this research. And I'd be happy to answer questions.
Thank you, Joe. So if there are any questions or comments, feel free to type them up in the chat box. We'll give it a couple minutes here.
Thanks, Bill. I have to.
Okay, well, Joe, I think you just did a job explaining everything, so I don't know if there are any questions going to be coming in. Um, your your contact information is on the Safe4Sim website. It's on the Hank Lab website too. I'm sure if you just search Joe Carney and U Iowa, you can find his contact information or Jody's information if you do have any follow-up questions.
I, I, I
Um,
I see that there's a group, some folks from Duke are here. I don't know if Michael's on or not. I know they're looking at warning systems as well for pedestrian road crossing. Um, I'd be really interested in hearing from anybody who has thoughts about warnings and the most effective ways to give pedestrian guidance about crossing. It's a problem we're really interested in and still hunting for the most effective ways to provide assistance to pedestrians.
okay, well, I think
Jody,
we'll save any other
did I
or
miss anything, Jody?
No, I think you got everything.
Okay. Yeah, great job. And I guess if there are any questions, they will contact you directly. So
Good.
thank you again for the pre.
Can I say one more thing? So this paper is in press, and a paper on this research is in press in Human Factors, and should be out in the relatively new future. So please keep an eye out for that. That will provide all of the details about the experiment and the methods and the results.
Excellent. Well, and we are getting our summer lineup of webinars scheduled and set up, so keep an eye out for announcements for upcoming ones. But this presentation will be online within the next few days, so you should get another email when it is posted so you can share it with any of your colleagues or anyone that is interested. So thanks again, Joe and Jody, for the presentation on the interesting work, and everyone have a good rest of your day.
Great. Thanks, Jacob.
Thanks, Jacob.
Thank you.